presenting efficient transformer, the evolution of the transformer, a technique that has now became one of the best techniques in AI recently. Probably the most versatile, but also very performing in many domains. And it's a big opportunity to share with all of you the new trends in the transformer with all of you. And sorry, I hear some audio back. And at PyCampus, the transformer has always been something very important to us. And I remember it was, I think, June 2017, where the first paper was published, Attention is All You Need. And I think it was about October that Lukasz, October 2017, Lukasz was here at the opening day of the Pi School of Artificial Intelligence, presenting this with a room full of people that wanted to hear about the transformer. And at the very beginning, it looked like a very interesting technology, and that's why we were super happy of seeing this, but we could not think that over the years was growing and continuously. So for us at the campus, we use it in multiple ways. Now, one way, probably the most important, is that translated. Since the paper was published, we have been switching from different kind of neural nets to the transformer for the machine translation engine behind translated. And we evolved the model. We built adaptive models around the transformer to be able to interact with translators. And the transformers has proven to be very versatile, super performance in machine translation. But that's not the only use case of transformer. And one of the things that Lukasz helped us, one of the first projects at the school was the OCR for the Vatican Secret Archive. And it was an incredible project done together with the University of Roma Tre. Lukasz was advising the two students of the school, and the result was a nice project that was in the TensorFlow homepage for over a year as a showcase. I think we were very proud, all of us, of the results of that project from the students. Elena, and I still thank Elena for the great work she did at the first session of the Pi School of Artificial Intelligence. And very few people know, actually, that the transformer is also the model behind GPT-3. So everybody's talking about these new, beautiful generative models. And honestly, it's a transformer, and with a lot of data and computation behind, probably about over $10 million of training. It's a great project, great applications, great results, but the technology behind is one of the things that Lukasz was co-author of. And so it's a great pleasure to have the opportunity to see the updates, what's new in transformer, especially in efficient transformer. So before I intro to Lukasz and I give the stage to Lukasz, one service note, so a few things. So number one, if you're listening to this talk, you're probably interested in AI, and remember, there is 3 things that are happening at PyCampus about AI. Number one, we just launched a research center, Imminent, here. And Imminent has got €100,000 of grants, so equity-free money that you can receive for researchers in the field of language technology. So if you have any project that fits the Imminent grants, please apply. There is €100,000 for you as a present. So no equity, no debt. It's really a grant. Second thing, if you're doing startups in artificial intelligence, PyCampus has already invested in 49 companies. So why not being the next one? You can apply directly in the website. We provide between 50,000 and 300,000 euro in investment in pre-seed and seed stage companies. And last thing, Pi School of Artificial Intelligence applications are open. So if you're interested and want to learn more about these new techniques, please apply to the school. So after having done my work in service messages, I'm super happy after more than 1.5 years that we cannot meet in person, to at least see Lukasz in video today and introducing us the efficient transformer. Thank you so much, Lukasz, and welcome.
Thank you very much, Marco. I'm so happy to see you, even if on the screen. I do hope physical meetings will come back soon enough. Thank you very much for the introduction. And thank you for founding the PyCampus. I think it's wonderful how it's developing and how many people are attending and how it's helping everyone. And yes, transformers. I'm very happy they worked out so well. So let me jump into and talk a bit more technically about that. And we can have questions later when we talk about this. So I will talk today about efficient transformers, which is what I've been working on recently. And this is, of course, not just me. The first part of this talk is a work with Nikita and Anselm. The second part is a work with even more people, with Akansha, Afros, Yoni, Henrik. It's even hard to enumerate all of them, and it draws on the work of an even larger group of people. So why efficient transformers? Well, first of all, it's maybe good to come back and think about why transformers, right? In 2017, which feels like a long time ago, but it's only a few years, people were already doing translation with neural networks, right? Before transformers came, NLP with neural networks was already a big thing. It was already a blossoming field, and what people were using were recurrent neural networks. RNNs were everywhere: translation, language modeling, all of the things where you'd use transformers today, you'd use an LSTM or a GRU. So how did RNNs work? Well, you had an input, like here is an example of a translation, and an RNN is a recurrent neural network. It processes word by word, goes from the first word to the second to the third, and so on, processes the input. And then there was even an encoder-decoder attention that the decoder, while generating next word, could attend to the encoder. And RNNs were working quite well already. They had two drawbacks. The drawback that was very apparent at the time was that they were slow, because they need to process everything very sequentially. There is a state of the RNN, so you process one thing, you need to update the state, process the other, and so on and so forth. So that was, the speed problem was very clear at that time, that it was not parallelizing, and that was the main motivation for transformer at the time. What turned out, though, to be an even bigger problem when the sequences get longer is that while you can propagate gradients for fairly long sequences in RNNs, say 50, 100 tokens, maybe a few hundred, it's really hard to propagate gradients in RNN for very long sequences of thousands, multiple thousands. So that's a problem that transformer solves, and we'll talk more about it. And it turned out to be actually probably the more important of the problem that are solved by transformer. So what is a transformer? A transformer is, again, an input-output sequence-to-sequence model that instead of doing the recurrent thing, has attention and self-attention layers. So on the left, I hope you can see this animation that will repeat, and we'll go through it. There is an input sentence in the top, and which is in English, and we want to generate a French translation. So what happens, you first embed the words with word embeddings, and in the layers of the encoder, every word can attend to every other word. That's what these arrows are denoting. So these are layers where the activations are attending to themselves, but everyone to everyone. And in the decoder, the same is happening, but you only attend things to the left. So you can attend the encoder and the previous words. And you can see this on the animation that it's attending the encoder and the words behind. So that's the transformer architecture. It it works, which was at the time actually quite to our surprise. Even on the translation on the English-German, which is a standardized data set, the RNNs were reaching blue scores, which is the higher the better, of about 24. When you push them, maybe 25 or 6, which was very good because methods before neural networks were only getting to like 22 maybe. So these results were very good, and even the baseline transformer got to 27 blue, which with way less training cost. So we were very surprised. I mean, the less training cost was expected because it's parallel. Since everything is attending to everything, it does not have this sequentiality. So we were assuming that it will train faster, but it also trained to much better results. And this has been confirmed. Like with bigger models, they train even better. And it's not just translation. So later, a model called BERT, which is bidirectional transformer, it's the encoder part, turned out to do really well on a set of NLP tasks. And you can see like LSTMs, which are RNNs, with some attention, they get to like 70. And then there is a 10% jump with BERT to 80, and then even improved BERTs, like bigger models or with recurrence, they get to 90. So this transformer architecture works not only faster, but also surprisingly better. And now that's why it's now used in so many different tasks. But does it have drawbacks? Well, it does, because at the heart of it, everything's attending to everything. As you saw on the picture, maybe let's go back here. When you run the transformer on a sentence, whether the encoder or the decoder, it's maybe easier to see at the encoder, every single token, every single word here is attending to every other word, right? These are the arrows that are happening. So fundamentally, this is an operation that is quadratic in the length of the sentence, which is not a problem if the sentence has 4 tokens like here, or even 40. But when you get to 4,000, 40,000, when you want to process whole paragraphs, this becomes prohibitive. And you can see an example here that this is not just a theoretical problem that it will become quadratic and prohibitive, but a really real problem. There is a BERT large model. Sequence length is the number of tokens in the sequence, and you see like 64 is okay, 128 is still fine. You can get to 300, and then if you have a 12 gigabyte GPU at 384, you just cannot fit anymore in memory because you need to have this square matrix. You could do tricks with it and still fit it in memory, but then it will run very slowly. So this is a big problem for transformers on long sequences. And there is another problem that it turns out transformers, the larger, the more parameters in them, the better. And when you grow them, they become very slow and they consume a lot of energy. So that's why efficiency is a key concern with transformers in recent years. And this is the example like GPT-3. GPT-3 is a transformer with 175 billion parameters. So the base one that I've shown you before, it had maybe 12 million. The large one had maybe 100 million. So this is 1,000 times larger. And you could ask, is there any reason to make them so big, right? Maybe we should not do that. Maybe we should stop at 1 billion parameters. And this is the plot that shows you that you should not, that there is a good reason to make transformers really big. Because when you jump from, you see 1 billion to 13 billion to 100 billion parameters, the performance, especially on like tasks where you have only one example, or you need to do things zero shot, like things that the model has not been trained very well to do, the performance on such tasks, which you do care about, because sometimes your users will ask things you have not foreseen, it improves dramatically with size. So you do want these big models, but there is a problem because they're really slow, really inefficient. They use a ton of memory. So that's the motivation for trying to make efficient transformers, because, you know, if we don't, then in the near future, the state-of-the-art, the really big models and really long sequences will only be doable at Google, Microsoft, and maybe a few companies, because no one else will be able to do that. And that would be a little bit sad. Like, we really like this to be something that you can run on your GPU, take a huge transformer models, run it over entire chapters of documents of text, say 1 million tokens at a time, and run it on a single GPU. Of course, you may not be able to train a huge model on like all of the web. The training process may just be very costly, but there are models uploaded that are trained. What you want to do is to fine-tune this model or be able to use it, decode from it really fast. So can we do this, right? Can we make transformers that are efficient, that would run on a GPU, even on very long sequences, and be efficient at decoding even when they're very large and fine-tunable on a single machine? And I believe this is the case, and I'll show you what is needed to do that. So we need to address the memory efficiency, because I'll show you, if you have a really large transformer, it will just run out of memory. And you can do that with reversible layers, which is an idea from 2017, again, used in image models, and it can be adapted to transformer, and this works. And then you can swap from GPU memory to CPU memory to save memory on the GPU, and in this way run on a single accelerator. So that addresses the memory challenge. Now, the time complexity, it's still a quadratic layer, the attention. So I'll show you how you can speed it up with locality sensitive hashing. And finally, if you need to activate all weights of the model and it's really large, then it will still be slow at decoding, because there is just so many weights to activate, to get from memory, multiply, get back. And this can be solved with sparse layers. This is a very recent work that I'll give you a preview of, where every token activates just a part of the weights, and it turns out it works really well. So let me show you how this can be done. Memory efficiency. So imagine you have an input of like really a lot of tokens. Let's say 1 million. 1 million is quite ambitious. Maybe 100,000 is enough. A long book will have maybe 200,000, but let's say 1 million for easy calculation. And transformer has this embedding size, which was called D model in the paper. Let's say it's 512. That's not a very big model, right? And GPT-3, it's like 4,000 or 8,000 probably. But even not a very big model, 512, 1 million tokens, that's already a tensor that takes 2 gigabytes. So that's a lot if you have a 12 gigabyte GPU. And you need to, every layer you go through, you need to have another tensor of 2 gigabytes, not to mention all the tensors inside the layer. So if you have 12 layers, which is also not that much, you already have 50 gigabytes of memory. So you'll run out of memory just by keeping these tensors, not even to mention what happens inside the layer. So that's bad. And you need to store them, because you'll backpropagate through them during training. Otherwise, you could just remove them from memory, right? So the answer to this are reversible networks. So transformer is a network that has residual connections, right? It takes an activation, runs a layer, and adds the output to the input. So instead of doing that, you can have these two lines of input. So at the beginning, you just make 2 copies of your activation. And then whenever you run a layer, so layer 1 here would be the attention layer, and layer 2 would be the feed-forward block. You run one layer on the one copy of the input, add it to the other copy, and then run the second layer on that copy and add it to the first. So this is a different operation than residual, but this operation can be reversed. So if you know the outputs, you can recompute the inputs, because you can just subtract the layer 2 from the second copy and then subtract layer 1, as is shown on the right side. So you can reverse it just by trivially running the layers in a different order, which means if you have the output, so now it's 4 GB because you need 2 copies, but then you need just one of this because you can recompute the input again and again. So there is no caching. You can just run forward with 1 copy, and then from the output run backward, recompute the inputs, and save a lot of memory. Even, we went from 50 to 4 GB even for this small model, and the more layers, the bigger your savings. So the question is, this is a little bit of a different model because it's reversible. So does it work as well as the standard transformer? And the answer is yes, it works. Here it shows that it may even work slightly better, but that may be that because it was better tuned, but it definitely works on par with the standard transformer. So you can make transformer reversible and it works well. And that's really good news for memory efficiency. Now, how about the time complexity of transformers? So the feed-forward block of a transformer, it has like a dense layer to a large intermediate activation tensors, and then a ReLU, and then it goes another dense layer to the output. It is linear, and we will not try to improve upon that at this part. But the attention, as you saw in the animation, it's a quadratic operation. So if you have a length L, it does L squared dot product operations because it creates these keys and queries using feed-forward layers on the activations, and then multiplies keys by queries. So this is an operation that is quadratic, but it is also an operation that is sparse in the sense every query will attend to only so many keys. Usually 1, as you see for the query 1 has 1, for the query 2 has 2. Some may attend to a few more, but generally it would not hurt if you limited this number. If you said there's only like 30 or 64 or whatever number that's convenient of the keys that the query can attend to, because it's meant to be sparse. That's why the softmax is here. So can we use this to make it faster? And there is an old idea in computer science that is how to make such searches faster, because what you're trying to get from the queries is the keys that are their nearest neighbors. So key 1 is the nearest neighbor of query 1, and say for query 5, key 3, 4, and 5 are the nearest neighbor in the cosine distance space of the query 5. So how can you get nearest neighbors faster than calculating all distances? So I'll show you, like, these vectors are in transformers are like 512 dimensional. It's a very high dimensional space, but here it's only 2D, right? So we can draw it. Imagine you have these dots, right? And say you want to calculate the nearest neighbor of one of these dots, say this one. So you can calculate distances to every other dot, right? And then say, oh, this one will be the nearest. But can you do better? Can you do it faster? And you can, and here is the idea. You draw a few random lines in the space. So here we have 2 random lines, and you will only consider things that lie on the same side of all these lines. So you will only consider for these 3 dots, you will calculate the distances to the nearest neighbors, but only for among these 3. And for these, you'll calculate them only among these 5. And here you'll only calculate them among these 4. And so you'll restrict the groups you're considering. You'll only calculate so it will be much faster because you're calculating distances only among the small group. And in most cases, you see the nearest neighbor will indeed be within this group because it's like close by. That's why it's called locality sensitive, because like when you divide a space with lines, things end up on the same side. Okay, so that's great, but as you'll see, sometimes it mostly works. It's a probabilistic algorithm, but sometimes it fails and you need to do something else. So how can you use this for attention? Well, assuming queries and keys are the same vector, you do this bucketing, which is you draw a number of hyperplanes and put things, the color are the bits on which side of the hyperplanes the activations are found. And then you sort by by these hashing buckets. And then to be efficient on hardware like GPUs and TPUs, you don't want to have, like, these hash buckets have very variable sizes, and you don't want that. So you quite brutally just cut it into the expected sizes, and maybe you attend things that are in your bucket and one before. So these are technical ways to make the implementation run fast. But there is a fundamental problem already in this hashing on the plane that you see this point. Its nearest neighbor is not blue, right? It's actually yellow. So you may be missing something. And the solution to this problem is to draw two other random lines. And for this point, as you see now, it's improved because with high probability, you will find one of these random things that actually is correct for every point. So you need to redraw in this algorithm, and we tested, like, how much do we need to redraw this hashing to make attention work as well as the full attention. And it turns out, like, when you get to around 8 hashes, it starts working very similar to full attention, at least. So this was image generation. And does it speed things up? Well, that depends how long your sequences are. When your sequences are like 2,000 long, it doesn't really speed things up much. It's kind of on par. But when they're 4,000 long, it's already better. And when you then go to 16, 30,000, it is much, much better, right? It scales linearly rather than growing. Okay, so that is the hashing attention, and this allows you to process really long sequences in a short time. And finally, what do you do? So we have solved the memory problem, we have solved the time complexity, but how about actually running these big models, right? So there is still a problem that if you have a model that has 100 billion weights, and these weights are usually mostly in the feed-forward block layer, then you need to activate, like, every of these weights will need to be pulled from memory to the CPU every single time. So here is how the feed-forward layer works. You have an activation vector, which is about d model of size, and then d model by DFF is the matrix where most of the weights of the transformer are. And DFF is usually like 4 times larger than D model, but it could be even like 8 times larger or 16. So it's a big layer. You do a matrix multiplication, then a ReLU, and then you do a matrix multiplication of the result with another matrix of the DFF by D model size, but now it's transposed. And that's the output of the feed-forward block. So how does a sparse feed-forward layer look? Well, you do the same computation, but you just assume that some of the middle outputs of this long vector that has a DFF size will be zeros. So some of them will be zeros because you have a ReLU anyway, right? So even if you train a normal transformer, some of them will be zeros. And the trick you do in the sparse layer is you predict with a much smaller network which ones will be zeros, and you don't even retrieve the columns of this matrix that correspond to those zeros. Because if you know this will be a zero anyway, then why bother retrieving these weights, which are d model by times larger? So you'll only retrieve these, say here, these 2 rows, and only calculate these 2 elements. But you need to predict beforehand, like, that these other ones will be zeros. And then once you know which ones are zeros, you also do the same trick for the other matrix. Okay, how can you predict which numbers will be zeros? And you only need to predict a superset. Well, you do this with a very simple idea. You take a low rank matrix, so d model by something really small, and this will tell you, then you have something really small by DFF, which is a large, but you make low rank here maybe like as small as 32. So there is something very small telling you which elements will be zeros and which elements will be 1. And so this is, though, a discrete operation. So there is something called a straight-through Gumbel softmax estimator that you need to use to to backpropagate error through this. We'll not go into it. But with that, you know a subset of these will be zeros, and then you can save on retrieving these weights from memory. And this works as well as the standard layer, but you retrieve on like 60 or 100 times less weights. So you have a sparse transformer, you retrieve 100 times less weights, but it will not work that fast because there are also dense layers in attention, and they have no ReLU. They are just like pure dense layers. So to make those layers sparse, you need a different idea. You need to take the activation vector and do something like a local convolution. You just split it into a number of blocks and run small dense layers for these blocks. So if you combine these ideas, you can get a sparsified transformer model, which has perplexity on par with the dense model of the same size. So that's the graph below. The blue line is like a transformer trained with the normal feed-forward block. And the other lines is like a set of different experiments with sparse QKB, sparse FF with 100 times sparsity, 60 times sparsity. And what you can see, like the magenta line with 60 times sparsity is actually even slightly above the baselines. So you get a model that gives you the same performance, but is over 5 times faster than the medium-sized model on decoding. And if you go to a really big model, this one is like 7 billion parameters, it's 30 times faster in decoding because it's even sparse. So that's these are results that are not even yet out. We'll be publishing them very soon. So where does this bring us? Well, I think there is a very promising future for transformers because you can make very efficient transformer models, and which means you can run a model on really long sequences, 16,000, 30,000, 50,000, meaning you can run them on even whole books, whole articles. Say you need to summarize an article, the transformer can just read the whole article or generate really long text, and it can decode. Decoding can be fast even on CPUs if you make the models efficient for that. So and fine-tuning, meaning training on a smaller problem, can be done even on a GPU at home. So I do feel that the use of transformers, thanks to these new efficiency improvements, will explode because it will be accessible for more and more people on more and more problems. And that's why I feel this work is so interesting. So yeah, that's I think that's what I wanted to present. And shall we go to questions? Hello.
Without the audio, here we are. Sorry, Lukasz, didn't have I was muted. So great, and I think we already have some questions that came from the audience, and you decide, Lukasz, if you want to keep the slides or if you want to remove the sharing for the questions. Okay, so some already came, and also Sebastian is collecting the other questions. So feel free to ask. He will collect and will come and do the question himself. So first thing, we wanted to ask something more general before getting into the specificity of the efficient transformer. Is how is the idea of the transformer? Okay, so the idea of attention. What was the inspiration coming from? So how did the idea of this new technique come from? So, and this for all the people that are listening to us, I think they ask this question because they would like to know how they can also get those kind of ideas. So what is the process that brings to a new concept like this?
Well, I would say we should always remember that the idea of, as I shown on the beginning slides, the idea of attention between encoder and decoder was already there in the RNNs, and it came there because it was actually, the attention is very similar to alignment in machine translation models, which has been used way before deep neural networks have been used there. So we always stand on the shoulder of giants. We should remember that the ideas don't come from nowhere, right? They come from the study of things that were there before. I feel though that there was the belief that you can try, like, you need to try things that may not obviously work, right? And it was a little bit, it required a little bit of courage to try to just have the attention, like that you will not, the very early transformer models actually had some convolutions together with the attentions. And we were thinking they may be necessary, and then we removed them. So we weren't that courageous also, but there were people saying, okay, maybe we don't need all of this recurrence. Maybe you just put attention and it will work, and it did. And so you should always try. You need to try things that are a little bit different than, like a little bit more different than what other people are doing. But on the other hand, try things that are founded in things that were before, like attention. Encoder-decoder attention was known to work, right? It was known to improve translation before transformers. So we knew it already works to some extent, but just trying just that was. I always feel like it's good to try these wild things, right? You will fail mostly, but sometimes it will work.
And that's very encouraging to hear that, because at the end, it's always like startups. The winners are the ones that try hard many things. And so here's again a confirmation of that. Great. So the second question.
You also need to learn the things before. Right?
Oh, yes. Yes.
It worked.
Yeah.
The idea that was there, right? The alignment that's been in machine translation for a long, long time turned out to be.
I think since the 90s it was there, yes. And so the other question we received just is that so there is use of transformer like in Google Translate, or we said GPT-3. Is there any other use that you're very proud of? Some things that you have seen around of usage of the transformer that you really like, I think are things that we also should be looking at.
I mean, there is a lot of use in NLP, right? There is BERT, which is used for representations. It's used in Google search. I'm very proud of the OCR usages. I'm very happy about that. Transformers are now used in vision, speech recognition. I'm very happy about all of these usages. Thinking forward, I also look forward to like longer context things, as I was saying. I feel like we're restricting transformers too much on the short sentences. We should give them whole paragraphs, whole articles, and see, whole files of code, we'll see what, but just more context. We have context for a lot of things, and these neural networks still don't have very much of it. And it's tricky in translation. I remember the translating tried, and on the metrics we have, it's very hard to measure improvement when you translate a whole paragraph instead of just sentence by sentence. You kind of know it will be better, but it's very hard to measure. So I feel like the metrics are not yet there. But you wouldn't ask a translator, you wouldn't scramble sentences around and give it to a translator. You would give him usually a whole paragraph. And the models are not getting this, so they cannot do much better. But we also can't measure quality at this level yet. So I think the work in improving metrics is also important, because
okay, very
blue scores don't cut it anymore, right?
Well, given the quality achieved by the models, blue score is no longer relevant. We need a much more high resolution metric for that, that's for sure.
It was an amazing metric for progress for a few decades, right? It
Yes.
really moved everything forward, but it's time for a new thing that we don't yet have.
Yes, in fact, the other question is very related, and people are asking when we will see a lot of use of the transformer in vision, in text-to-speech, or speech recognition, because at the end also the efficient transformer, no, it's something that can now be used to also solve these problems efficiently.
Oh, and I think there is a lot of use. Vision transformers are getting very popular this year, I feel, and because they've also shown improvements on benchmarks, and people are seeing they're really good. In vision, of course, they're not pure transformers. There's often you add things a little bit vision specific, and that's fine. I do think speech recognition is also using transformers more and more. So, so these things are seeing more and more use. I never thought you need to be very pure, right? If a convolution in the first layer helps your vision system, you can keep it. It doesn't need to. You don't need to remove everything if you're building a system that someone will use. But it's nice conceptually to know that you could, right?
Okay. And now, before I move to Sebastian with some technical questions he received, so I have a difficult one. Okay. Now, so is there any other model technology that you fear, that you don't sleep at night because you think that there is this new technique that eventually will become better than the transformer very soon? Is there something that worries you, but that we should be looking at?
I wouldn't worry. I would be super happy. It's time. It's time, right? These techniques are meant to be improved upon. There is recently there were like papers saying maybe you don't need attention at all. In some ways, like Fourier transforms seem to do something very similar that can substitute for attention in at least some cases. So I'm very excited about these techniques. As I say, I never think you need to be so pure if you're building systems for people, for like a startup. It's different when you're writing a paper. When you're writing a paper, you want a single idea that's very clear. But if you're building a system for people, for customers, you want to mix all the best things you can. So the more, the better, right? The more you can have, the better you can be. I don't see just yet an idea that could replace attention everywhere for all problems. And I'm not sure it will come, but it might. We don't know.
Okay.
It's I do think there is also interesting ways to use attention that have not yet been tried, because we only do this attention to every thing. So Jeff Hinton recently had this GLOM paper, which is more often like a set of ideas that you can pick from, where he suggests different ways of you could call it an attention, but it's different things are attending different things, but do you have whole islands of things that are the same.
And do you mean capsule or something new that he proposed?
It's an evolution of capsules, I would say. It's called GLOM, G-L-O-M. It's a very recent thing that was published, with a very interesting idea that you have a lot of vectors that are the same that represent things. So there may be ideas that replace attention, but there may be ideas that just use attention in different ways. It's still a very exciting field to look at.
Perfect. Okay, I see Sebastian is here with more questions, and so I leave the room to Sebastian to ask you more questions, and I think they're getting more technical and technical.
Thank you.
Grazie.
Hi, Sebastian.
Hi, Lukasz.
Hi.
Nice to be with you. Thanks. So yeah, I've been collecting a couple of questions both on the YouTube channel where this is playing, and also questions that we received from people before. So I've got a couple of minutes left, I guess. Yeah, 10 or so minutes. So I'll try and pick out a few. One is, can you actually reveal where the paper will come out?
Oh, hopefully Monday.
Oh, okay. So that's okay. Super. It's really close to the time then.
I mean, there's a URIP submission deadline on Sunday, so it's not, or Friday, sorry. So then there is archive time. So it's, I think a lot of interesting papers will come out
on Monday. Yes. So yeah, watch archive on Monday.
Well, on Tuesday. Watch archive all of next week. It's always after a big conference deadline that there is a whole slew of papers.
Makes sense. Okay, and so then
I don't know if this is the best way actually it should work, but this is the way it still works.
Well, and surely to all those people who've been waiting for the paper that accompanies the talk you've given today, this is the go-to place, I guess. So many people asked about several technical questions about transformers and variants of transformers, I guess. So some asked us, in practice, are there any good alternatives to fine-tuning in practical use again? For instance, are there any suggestions, any good things to do or tips for few-shot learning and semi-supervised use of transformers? Any hints in these directions?
So there are there are recently results that show you can fine-tune. Like, you don't need to fine-tune all the parameters. You can fine-tune, like, literally have like 60 vectors that you just concatenate at the beginning of the word vectors, and you only fine-tune those for the tasks. And it works as well as fine-tuning everything. So that is promising, because you can have like one copy of the big model that you're not touching, and you're just fine-tuning a tiny bit. But it's still fine-tuning, so you still need to run training through that. It does make, like, you could make an API that just, you can store one copy of this huge model and then just 1,000 copies for different tasks of these, or different users of these vectors. So I think that's very promising. I mean, GPT-3 can do zero shot, and that's super astounding how good it works, but it still works better if you fine-tune a little bit. So I would still believe that fine-tuning, like, at least a part of your model is a good idea. It's more of an engineering challenge. How can you do this? Like, things we've shown that you can do this on your own. Yes, that's still a challenge. But
okay,
but
makes sense. So you were one of the main authors of Tensor to Tensor at the time. Now Trax has taken over. Can you comment on, and many people asked us also about, where do we find pre-trained models for that? Can we reproduce these things and so forth? So do you mind taking a second to speak about how Trax takes over some of the goals you had with Tensor to Tensor and how it does that job?
Yes, we never released that many pre-trained models, even in Tensor to Tensor. We'll certainly release some in Trax. It's a huge amount of work to maintain pre-trained models so that they're compatible with the next version, so that you make sure they work on the hardware. Some other frameworks changes, then they may run out of memory. So it's a little bit too much work for we're mostly researchers. It requires more of the support, and I feel like these days Hugging Face has taken the burden and the price coming with that of maintaining large body of pre-trained models. Most of the talk today was based on Reformer, which was immediately integrated into Hugging Face. The model, the sparse model, we call it Terraformer. That will probably not be on Hugging Face next week, but I really do hope that it will appear there soon. And I'm very, I'm super happy about the work Hugging Face is doing to maintain this all. But you need a whole company, a lot of people to maintain these things, and it's great they're doing this.
So you're counting. You're saying you're counting on the ecosystem, in a word.
Yes, we work with these pre-trained models. To me, I do feel there are still ideas and frameworks like Trax that make research really easy in many ways. The Trax is based on combinators, but with a stack system that I feel are much better than like the Caffe or Torch combinators at this point, and I do hope this will spread. I feel like Tensor to Tensor has spread a number of ideas. It was some inspiration for parts of Hugging Face. It grew TFDS and then the Hugging Face NLP data set, which came out of it. So it's to me, it's about like there are some good design ideas in code that later spread, while whether it's this or that code base, let's say, will probably not stay as long as Emacs. But very few projects, very few code projects live that long, right?
Mm-hmm.
But the ideas in them live on in other projects. Mm-hmm. On the other hand, I feel like for my work, it's still for research, it's still the most convenient tool I find. So
cool. Okay. Thanks. Let me just, because I'm looking at the watch and we have time for just a couple more questions from the audience again. So several people were asking about this work about FNet, also Google Research. So, I mean, there's this magic, looks like magic. You replace self-attention by simple linear transforms, Fourier transforms, and it works almost as well, much faster. What do you think of all this work? Is this something that can be scaled up, can be continued?
Well, it needs to be tried, right? It definitely works great on some tasks. It's not clear to me it will work as well as attention on some other tasks, but it might. We just don't know. But we didn't know when the transformer paper appeared. We had no clue it will work so well for summarization, for example. It was just never tried. But we did hope, and so we should hope about FNet. And it might. I like summarization because summarizing long things like there is a data set of archive articles where you take an article and generate an abstract, right? That's how the data set is generated. It's a really hard task because you need to take this input that has a lot of words, 10,000 at least, right? A whole article, and generate something that's also not just one sentence. And there are, like, Pegasus is a model that does really well on that. So it's a task that can be done and it's a tougher test than for some of these attention mechanisms that are not very, like the hashing attention can attend. Like if you need to pick out a name from an article and copy it, it's very easy for it. For the Fourier transforms, it may be harder when the sequences are longer, but maybe not. There's only one way to know. Someone needs to try it, right? That's the.
Essentially, you're saying all these models have got their own inductive biases, but we can't guess, before experimenting. It's just beyond us to guess them.
We need to try. That's the beauty of deep learning. You can be the one who tries it. Just go and try, and we'll see.
Beautiful. I guess that's a great finishing message. So just before saying goodbye, I just wanted to sort of send out a message to everyone who's listening to us here again, repeating what Marco pointed out at the beginning, so opportunities that are out there. We at Translated, we have opportunities for researchers who are working on language technology. We have Imminent, this research center that we just opened, and we've got grants out, so 100,000 euros in grants. So you can visit our webpage and check out if you'd like to apply for one of these. If instead you're a founder, you're launching a startup in AI, then PyCampus has already made 48, or is it 49? 49, investments in applied AI, and so maybe you want to be the next one. So pycampus.it is a place to go to. And if instead you're still learning AI, then why not apply to School of AI? So the website to go to here is pycampus-school.com. The next batch of School of AI will be hosted, I guess, in the fall, so Q4 2021. So that's 3 opportunities according to whether you're a researcher, a start-upper, or you're learning AI. And well, with that, and we're just on time, everyone here, Lukasz, audience, and people around me alike here would like to send you a very warm thank you.
And thank you very much too for organizing this and the invitation. Thank you, Sebastian. Thank you, Marco. Goodbye.
Thanks, Lukasz. Bye-bye.
Bye-bye.